Welcome to Brain Vision.
The force that is acting on this we can find by using one of the formulas that we should have learned earlier, which is the negative potential is equal to the antiderivative of the force function with respect to position. So this right here can be rearranged in such a manner that the force will be solved for, and it will equal the negative derivative of the potential energy with respect to position. So taking the derivative of our potential function here, we will have to use our power rule and reverse it. So du dr, negative du dr actually, will equal, forgot I wrote it here, the A will come out and stay, and we would have to reverse the power rule on 1 over r to the 12th power. That will give us 12, or negative 12. Actually, let's bring the negative outside, just to make things more neat and organized. So that is a negative from our potential and force relation here. So we take the A out, and A over r to the 12th power is actually equal to A times r to the negative 12th power. So the derivative would be A times negative 12 times r to the negative 13th power, due to the chain rule, or the power rule as many call it. So we can write this as negative 12 times A all divided by r to the 13th power. Okay, and now we have to take the derivative of our second part right here, and that would be negative or minus negative b divided by r to the 6th power, or now it's 7th power, and then multiply 6 here, and these two will actually cancel. So our force will be equal to 12a over r to the 13th power minus 6b divided by r to the 7th. And this right here is our force. Great. Now the second part asks us to graph these. So let's graph the force function first. Our force function, when graphed, will look something like this, without actually touching 0. This is with respect to r. Why doesn't it touch 0? Well, because if r equals 0, then we would have a 0 in the denominator, and this is not allowed. Now to graph the potential with respect to r, we would have to graph something that looks like this. Again, not touching the r equals 0, because r cannot equal 0. No 0 in denominators. Great. The next part of the question asks to find the distance the distance when it is at equilibrium, meaning the net force is equal to 0. Well, since this force is the only force acting on our particles, we can use that as the net force. So if we set this equal to 0, we would have 0 equals 12a over r to the 13th minus 6b divided by r to the 7th. Now, right off the bat, we can cross off the r to the 7th here and subtract 7 from here, because that would be the same as multiplying r to the 7th on both sides. And this will just go away. Anything multiplied by 0 is 0. So that will leave us with 12a divided by r to the 6th power minus 6b is equal to 0. Now we can divide both sides by 6, and that would give us with a similar result as the previous one, that we will get 2a divided by r to the 6th power is equal to b. So to solve for r, we would have to multiply r to the 6th power on both sides. So you can cancel the bottom r. Divide both sides by b. Great. So to sum everything up, we will have 2a over b is equal to r to the 6th power. So to get rid of the 6th power, we would have to put everything to the power of 1 over 6. And this right here will give us our distance, which is equal to 2a divided by b to the 1 over 6 power. Great. Ooh, what is that? Okay. This right here is our distance. Now we would like to know where the variable we just found, distance, would be, well, we would like to know what the energy would be for this distance right here. So we would have to plug this r value right here into the position, or not the position, the potential energy function. So doing so, we will simply get a divided by, well, if we put 1 to the 6th power inside of to the power of 12, we will actually get to the power of 2 instead, because 1 over 6 times 12 is equal to 2. So we would have to put 2a over b to the 2nd power. Now for our second part, it's minus b over, again, we have r to the 6th power right here. So we would have to put this function to the 6th power, canceling out the exponent. And that would leave us with 2a over b. This can be simplified to, well, a times b squared divided by 4a squared Again, this will cancel right here. I'll just do this for now. Minus b squared over 2a. Since we want to make the denominators the same, we would have to multiply 2. And that will give us 4a on the bottom. This will equal negative b squared over 4a. And this right here is our potential energy. Great. So our final part of the problem is to, well, they give us that the dissociation energy or the dissociation energy is equal to 1.54. Oh, looks like a 9. I'll redo that. 1.54 times 10 to the negative 18th power. So to prove this, to prove our energy, we would have to use what we found earlier. So if this is the energy that we need, we would have to plug it in to our b squared over 4a equation. Or, oh wait, we have to find the equilibrium distance first. Oh, my bad. So if it says the equilibrium distance, if it gives us the distance is 1.13 times 10 to the negative 10th power, tongue twister there, we would have to put, well, we have our distance formula. Distance is right here. So we can use this once more to solve. So this will equal 2a over b to 1/6 power. So putting both sides to 6th power, we'll cancel this out. And now we will have to solve for a. So we multiply b to both sides to cancel out the b, and then we divide by 2 to cancel out the 2's. So our a will end up equaling, if you plug this into the calculator, we will end up getting 1/2 times, actually no, we can just leave it like this. So this is our value for a. Or to simplify it a little bit, make it neater, you'll have b over 2 times 1.13 times 10 to the power of negative 10 is equal to a. And that is our value of a. So now we have to I'm looking back at the problem. Oh, we have to use the dissociation energy, which is 1.54 times 10 to the negative 18th. So we know that the energy required is this right here. So we can just set it equal to the formula. But we solve for a. We know what a is. We can put everything in terms of b. So putting everything in terms of b, we will have b squared divided by 4 times a, which is everything here, and this too. So b squared, or b over 2 times 1.13 times 10 to the negative 10. Oh, I forgot the 6th power. Great. Now we can multiply both sides. Since the b's cancel here, we can multiply both sides by this value, by the bottom value here, and that will give us, if we put it in our calculator, b will be, I'd say, approximately 6.41. Is that what it says on my calculator? Yeah. Times 10 to the power of negative 78. It is okay to round significant figures. It's what we encounter daily in our scientific lives. Okay, since we found b, we can plug in the b value for a. Simply plug in the b over here. And doing so, we will get, let's see, plug it into a calculator, divide this by 2, multiply it by 1.13, 10 to the negative 10th, everything to the 6th power. A will be approximately 6.67 times 10 to the, oh, that's a big amount. Okay. Times 10 to the 12th power. And this right here is our a value.